Assalamu alaikum wa rahmatullah. Welcome back, my dear students. In this video, we are going to study part 4 of Kinematics 1. Our objective in this part is to determine the characteristics of the instantaneous velocity vector. Let's remember the main ideas of the previous part. The displacement vector delta r between t1 and t2 is the vector that connects the initial position with the final position. Delta r is equal to r2 minus r1, and the magnitude of delta r is different from the length of an arc. The average velocity vector is equal to r2 minus r1 divided by delta t, and its magnitude is equal to the magnitude of the displacement vector divided by delta t. And finally, the average speed is equal to the length of the an arc divided by delta t, and keep in mind that the magnitude of the average velocity is different from the average speed. Let's remember from math some rules of the derivative. Try to guess them alone. Now we are going to apply on these rules 3 examples. Remember that u is a function of t and t is our variable. Example number 1. V is equal to radical t squared. Note that this function has the shape of radical u, where u is equal to t squared. First of all, we have to find the derivative of u, which is 2t. Then, substituting it in its equation, u prime divided by 2 radical u, it will give 2t divided by 2 radical t squared, which is equal to 1 divided by t. Example number 2. If v is equal to t squared plus 1 all squared, notice that this function has the shape of u squared, where u is equal to t squared plus 1. First of all, we find the derivative of u, which is equal to 2t. Then, by substituting it in the equation nu prime u power n minus 1, it will give 4t into t squared plus 1. Example number 3. V is equal to cosine 6t. V is equal to cosine u, where u is equal to 6t, and u prime is equal to 6. Therefore, v prime will be equal to minus 6 sine 6t. How can we benefit from the derivative in physics, and especially in studying the velocity vector? Let us see. Consider a point M, which is moving on an arc of a circle. The points M1 and M2 are taken to be 2 points on this arc, representing 2 different positions. R1 is the position vector corresponding to M1, and R2 is the position vector corresponding to M2. The displacement vector between these 2 points is defined by delta r, which is equal to m1, m2 equal to r2 minus r1. The average velocity vector between these 2 points is equal to delta r divided by delta t, and its magnitude is equal to the magnitude of m1, m2 divided by delta t. The average speed is equal to the length of the arc m1, m2 divided by delta t. Note that the length of the arc is different from the length of the chord, and it is greater than it. Therefore, the magnitude of the average velocity vector is different from the average speed. But when does these 2 quantities be equal? Notice that when m1 and m2 are far from each other, then the length of the arc is different from the length of the chord. But if they are near or close to each other, then the length of the chord is approximately equal to the length of the arc. That means when t2 tends to t1 or when delta t tends to 0, then m1 and m2 are approximately confounded, and the length of the chord is equal to the length of the arc, and therefore the magnitude of the average velocity vector is equal to the average speed. Now let us name the line that joins m1 and m2 B, and let us draw another line which is tangent to the circle at point m2, and we name it A. If m2 gets very close to m1, then, as you can see in this figure, that the 2 lines A and B are confounded. Remember that the average velocity vector is equal to the displacement vector divided by delta t. then the direction of the average velocity vector is the same as the direction of the displacement vector. So in this case, and because displacement vector is now tangent to the circle, then also the average velocity vector is tangent to the circle. At this level, we define the instantaneous velocity vector as the average velocity when delta t tends to 0. Note that the instantaneous velocity is the velocity vector that helps us to study and describe the motion of an object at each instant. Therefore, we conclude that the instantaneous velocity vector is the limit of the average velocity vector as the time interval delta t approaches 0. The limit of the average velocity is the limit of delta r divided by delta t as delta t tends to 0. Delta r is the displacement vector between the two instants taken to be t plus delta t and t. And we know from mathematics that this limit is known as the definition of the derivative, which is defined by dr divided by dt, which is equal to r prime equal to x prime I plus y prime j. This is called the instantaneous velocity, denoted by v instantaneous or simply v. Let us now solve this example where our objective is to determine the instantaneous velocity and its magnitude. So let r be equal to ti plus t squared plus 1j. According to the formula, v instantaneous is equal to the derivative of r. This will give t prime I plus t squared plus 1 prime j. Therefore, r prime will be equal to 1i plus 2dj. 1 is the x component or vx of the instantaneous velocity vector, and 2t is vy or the y component of the instantaneous velocity vector. What about its magnitude? We have to apply the formula radical vx squared plus vy squared, which is equal to radical 1 plus 4t squared. Pay attention that to determine the magnitude of the velocity, we have to find the derivative of r first of all, and then substitute the instant in v. Application number 1. Given a particle's position vector as a function of time, determine its instantaneous velocity. Please pause the video, try to solve them alone, and then check your answers. Now we are going to study the characteristics of the instantaneous velocity. Let us take this example. As the moon rotates around the Earth, it describes an elliptical path. Let v1, v2, v3, and v4 be the velocities at 4 instants t1, t2, t3, and t4 respectively. As you can notice that the instantaneous velocity is tangent to the trajectory at these points. Note that if the path is straight or rectilinear, then the velocity is along the line. What are the characteristics of the velocity vector? Let m be a moving particle in a Cartesian system. Its velocity vector at instant t1 has the following characteristics. Its origin is the position of the particle. Its direction is tangent to the trajectory with the direction of motion. And its magnitude is radical vx squared plus vy squared. Now we are going to learn how to represent the instantaneous velocity vector. In a Cartesian system, the components of the velocity vector are its projections on x-axis and y-axis. For example, if r of t is equal to ti plus t squared j, then the instantaneous velocity vector is equal to I plus 2tj. It has two components, vx and vy, where vx is equal to 1 and vy is equal to 2t. If we want to represent the instantaneous velocity vector at time t is equal to 1 second, then first of all we have to find the magnitude of its components. Vx is equal to 1 meter per second and Vy is equal to 2 into 1, which is equal to 2 meter per second. We use the scale 1 square corresponds for 1 meter per second in order to draw Vx and Vy. This is Vx and this is Vy, and then in order to draw the instantaneous velocity vector at this instant, we have to notice that it is the diagonal of the rectangle formed by Vx and Vy. Let's take another example. If r of t is equal to ti minus t squared minus 5j, the equation of trajectory is y is equal to minus x squared plus 5. Therefore, we know that this trajectory is parabola and we can plot it. We want to find the instantaneous velocity vector at time t is equal to 1 second. Then we have to find the position of the particle at this instant. We substitute 1 in the position vector in x and y, and this will give x is equal to 1 and y is equal to 4. We name this point A, and then we plot it on the figure. Then A has coordinates 1 and 4. The instantaneous velocity vector is equal to I minus 2tj. Then its components are Vx is equal to 1 and Vy is equal to minus 2t. At the instant t is equal to 1 second, Vx is equal to 1 meter per second and Vy is equal to minus 2 as an algebraic value. The minus sign here tells us that this vector has opposite direction of the y-axis, but its magnitude is equal to 2 meter per second. We have to use the following scale in order to draw Vx and Vy, which is 1 square corresponds for 0.5 meter per second. Here we draw Vx and then we draw Vy, and as we have said before, V is the diagonal of the rectangle formed by Vx and Vy. Take another instant, which is at t is equal to 0 seconds. We find that the position of the particle at this instant was x is equal to 0 and y is equal to 5. We name this point B. So B has coordinates 0 and 5. What are the components of the velocity vector at this instant? Let's calculate them. Vx is equal to 1 meter per second and Vy is equal to 0. Using the scale 1 square corresponds for 0.5 meter per second, we draw Vx. Vy is equal to 0 in this case. Therefore, V and Vx are confounded and V is parallel to the x-axis as you can see in this figure. Let's solve now application number 2. The position vector of a moving particle is given by r is equal to OM, which is equal to 6ti plus 2t squared plus 2t plus 3j. The first part is we have to determine the position of m at t is equal to 0 seconds. Then we have to substitute t is equal to 0 seconds in the position vector, and that will give 0i plus 3j. Therefore, the position of m is 0, 3. In part 2, we have to determine the parametric equations, which are x is equal to 60, y is equal to 2t squared plus 2t plus 3. In part 3, we have to determine the equation of trajectory of m. T is equal to x divided by t, and by substitution we find that y is equal to x squared divided by 18 plus x divided by 3 plus 3. In part 4, we have to determine the average velocity vector and its magnitude between the two instants t is equal to 1 second and t2 is equal to 2 seconds. First of all, we have to find the position vector at these two instants. At t1 is equal to 1 second, r1 is equal to 6i plus 7j. And at t2 is equal to 2 seconds, r2 is equal to 12i plus 15j. And delta t is equal to 2 minus 1, which is equal to 1 second. The average velocity vector, which is defined by delta r divided by delta t, is equal to 6i minus 8j. The magnitude of this vector is radical 6 squared plus 8 squared, which is equal to 10 meter per second. In part 5, we have to determine the instantaneous velocity vector and its magnitude at t is equal to 3 seconds. First of all, we know that the instantaneous velocity vector is the derivative of the position vector. Then, v will be equal to r prime, which is 6i plus 40 plus 2j. Now we substitute t is equal to 3 seconds in the equation of v. It will give 6i plus 14j. Its magnitude is radical 6 squared plus 14 squared, which is equal to 15.23 meter per second. The summary. The average velocity vector, which is delta r divided by delta t, equal to r2 minus r1 divided by t2 minus t1, measures the variation of the position vector during an interval of time delta t. whereas the instantaneous velocity vector, which is defined by the derivative of the position vector equal to x prime I plus y prime j, measures the variation of the position vector during a very small interval of time that tends to zero. The characteristics of V are origin, position of the particle, direction, tangent to the trajectory with the direction of motion, and magnitude is radical Vx squared plus Vy squared. Thank you for watching. Please repeat this video more than one time in order to understand all the information that we have explained.